So today we're going to be talking about solving a systems of equations by graphing. We have already talked about how to graph linear equations, so we're going to build upon that and talk about how we can use those graphing strategies to solve a systems of equations. First, we need to know what is a systems of equations. So it's when you have two or more equations using the same variable, and your answer is always going to be an ordered pair. So when we graph them, we're going to see where our two lines touch. However, as you see in the last bullet, there's three possibilities. So some of our lines may not touch, or they may touch the whole way through. And I'll show you what I mean when we get to those examples. So first of all, intersecting lines. So when we have these two systems of equations, we're first going to graph them in slope-intercept form, which you know is y equals mx plus b, and where these two lines touch, that is going to be our answer. So for example, we graphed two lines already. I noticed that these two lines intersected or touched at the ordered pair 1, 2, so my answer for this system would be the ordered pair of x1 and y2. So that was our first possible solution. Your second one is if you graph parallel lines, and you can see the example right here. When we graphed, I noticed that these two lines did not touch, and they never will. They're going to go on forever and ever. So they do not touch. That means I have no solution for this systems of equations. There is no place that they would intersect. An easy way you could tell without even having to graph in the future is if your slope is the same for both equations, but you have different y-intercepts. So that's when you will have parallel lines. Same slope, different y-intercepts. The third and last possible answer for systems of equation is when you graph the two equations and they turn out to be right on top of each other when they're in slope-intercept form. So if you notice, I have a red line and a blue line, and they're directly on top of each other. That means they intersect or touch everywhere. So I have infinite solutions. They're always going to touch. I have infinite possibilities of ordered pairs that I could use as my answer. Another way to tell this is if they have the same slope and same y-intercept. So both of the equations look exactly the same. So that is our three types of possibilities. One ordered pair, no solution, or infinite many solutions. Okay, so here's the 4 easy steps, and I'm going to go through one example with you. You first need to convert the equations to slope-intercept form. So if you see them in standard form, they both need to be in slope-intercept form. You're going to graph them. Then you're going to identify the ordered pair where they touch, and then you need to check. So for this unit, you should be able to get 100 before you turn this in, because you can check all of your answers. Alright, so we are going to first find the solution for these two equations when we graph them. However, I have a problem. This is standard form. I cannot graph either one of these equations yet. So the first thing I need to do is put them in slope-intercept form. So I need to get y by itself. I need to move this 2x to the other side. I see my x first. I'm going to subtract my x first. This is a positive 2x, so that means I'm going to subtract 2x from both sides. Now, the 4 and 2x are not like terms, so I cannot combine them together. So I'm just going to write what I see. I see a negative 2x, because we subtracted the 2x, and that's a positive 4, so I have a plus 4. So my slope for the first one is negative 2, so that means I'm going to rise 2. I need to write it as a fraction, so I can always put it over 1. I'm going to run 1. And my y-intercept is that positive 4. You need to write it as an ordered pair. On the y-axis, or when x is 0, my y value would be 4, because that's the number at the end of my equation. On the second one, again, I see my x first, I subtract my x first. Also, I'm subtracting because it's a positive x. The opposite of a positive is a negative. Try to move it to the opposite side. Do the opposite. I still have this negative y, and again, you cannot combine these two terms. So I'm just going to rewrite what I see. I see a negative x, positive 2, or plus 2. Okay, y is still not by itself. This number that's really in front of y is a negative 1. these two things are being multiplied together. So to get rid of multiplication, to get it to the opposite side, I do the opposite. The inverse of multiplication is division. I'm going to divide both sides by a -1. So now this is gone. Finally, I have y by itself. So this is a -1x divided by a -1. Negative over a negative makes a positive. +2 divided by -1 is a -2. So my slope, my number in front of x, there's really a 1. So I would rise 1 and run 1. And my y-intercept, or this number at the end of my equation, is a -2. So on the y-axis, my starting point would be at -2. So that's just a little review of how to put these in slope-intercept form. Now let's see what happens when I graph them. So if you notice, this is what our standard form was. This is in red what our equations turned out to be once I put them in slope-intercept form. On my first equation, y-intercept was +4. This is where I started at +4. Then since it was negative, you go down 2 over 1 and you follow the pattern. You don't just go down, you also go up, but it went off the graph. And for the second one, my y-intercept was -2. Slope is 1 over 1. Right here is where my two lines touch. So this is my first type of solution for the systems of equation. Now they touched at the ordered pair 2, because on my x-axis I went to the right 2. I didn't go up or down at all, so my y value is 0. So the final step is to check your answer. So my ordered pair was 2, 0. I'm going to take this x value and plug it into the x. Take my y value and plug it in for the y. Solve this side. If it equals 4, then this is the correct solution. And it did. 2 times 2 gave me 4, plus nothing, still 4. So 4 would equal 4. However, it has to work for both equations, so I also have to plug it into the second one. So again, I'm going to take 2 and plug it in for x, minus my y, or 0. See, does it equal 2? Again, it does. 2 minus 0 is still 2, and my equation originally said it did equal 2. So we do, in fact, have the right answer. So this is just one example of how to solve systems of equations by graphing.